Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to this lecture on this solid state NMR part of it, which I have been talking to you some examples in the previous class. Let us continue with those examples before we go to the paramagnetic NMR in this. So in the previous class we have looked at various examples of just magic angle spinning followed by the different homonuclear decoupling kind of things. Then cross polarization with the different time scales, etc. So dipolar decoupling. So all these techniques that we have looked at, homonuclear decoupling, heteronuclear decoupling, and in the heteronuclear you have the one of the nucleus being the quadrupole. So all of these we have looked at. So let us continue. This NMR spectroscopy of this can be extended to the bioorganic chemistry, particularly the proteins and enzymes. If you look at the case of the enzymes of lactalbumin class and the lysozyme class, there are two. So if you look at these two and look at the literature that is known on this, what is derived is for these two, the origin for the emergence of these proteins is the same. In fact, one could address this from the NMR studies as well. And in these proteins, you have several centers where metal ion can bind. Of course, the lactalbumin is a calcium binding protein, and besides calcium binding, you can also have other ions binding to that, to these ones. So that is where what we look at this particular proteins in terms of that. So here we have a calcium binding NMR, calcium 43 NMR, both for the lactalbumin and also for this the lysozyme. So you can see that the lactalbumin from bovine, and so you can get this the split of the two in this, and similarly for the lysozyme, and when you apply these quadrupole coupled systems. So this is measured for the 43 calcium when you saturate this to a level of 0.9 to 1 equivalent of calcium salt, or in the other case 1.1 to 1.15 equivalent amount of calcium. So one is coming over here, other is coming over here. So this is for the lactalbumin and this is for the lysozyme. You can see there. In fact, in these calcium binding proteins you have a different regions of binding, but that doesn't become a part of this particular course. If you read somewhere you will know something called EF hand binding, and you have another region loop binding, and various other bindings. So in each binding the calcium environment is not the same. Okay, so therefore the calcium interactions with the neighbor, the quadrupole coupling values will vary. Now if you look at the quadrupole coupling values, which is chi, this is the chi 1.3, you get one particular site in the cal binding site, and another site where you have a chi is 0.7 to 0.8, quadrupolar coupling is little less, and that comes from a different region. So different region bound calcium to this protein, because you are adding excess amount of calcium while measuring this, that is like 0.9 to 1 equivalent or 1.1 to 1.15 equivalents of calcium you are already adding, and that calcium binds to two different regions, and one of those regions has got a greater quadrupolar coupling, and that's coming slightly higher in this negative side, and 0.7 to 0.8 is coming here. EF hand region, it's coming here, and this is for the trypsin. So different the calciums which are bound to this protein exhibit different levels of quadrupolar coupling, and that is indeed reflected in the chemical shifts of that. So therefore using this particular NMR technique, you can find where this calcium is binding in the protein. What is the vicinity? So by looking at the quadrupolar coupling values, by combining other informations of calcium binding strengths, which comes from the ITC and other studies, you can evolve with a model where the calcium is binding and the structural aspect of it. And that's what is written over here. So here you can see the calcium 43 chemical shifts and quadrupole coupling constant are highly sensitive to the chemical nature, the geometry of the calcium 2+ coordination sphere. So therefore, it's both the what kind of a groups, how many such groups, what is the geometry. So all of these, they influence the chemical shift. So in other words, chemical shift is a parameter that is being varied because of all these. So therefore, here in the B we have shown that the data for all of these, and then EF-HAN, paraalbumin, there's another protein, calmodulin and troponin. So in all these, the EF region will come here and the other parts of the regions will come there, and cal binding portion comes here. Don't worry about this D9K, etc. The pseudo EF-HAN cal binding comes somewhere here. So all of these, and the W loop in the beta trypsin here. So they have different vicinities, different geometries, different number of coordinations. So that is why they are coming differently. As a result of that, NMR can be used to quantify these regions in this protein. And in addition, if you use some binding strengths from other techniques, you can evolve with the structural aspects of it. So this is one class of proteins. Let's look at another class of proteins called transferins. Transferins are the iron carrying proteins. The iron is being carried through the blood to different organs of the body, and that is where. So now these proteins still have a lot of sites where the metal ions can bind, etc. And then of course we know that the allosteric factor is carbonate in this, and the carbonate is also provides a center for the metal ion binding. Now here is a situation where a C13 NMR and aluminum 27 NMR, aluminum of course quadrupole nuclei. So these are done. Now let me tell a little another piece of information regarding the transferins. The transferins have got two lobes, which is called the C-terminal and N-terminal lobes. Okay, so you can basically call as a two halves of it. So half, when you read this, you find the two halves. So half molecule means it can be in the C-terminal half of it or N-terminal half of it. Okay, so that is where it is shown as the OTF, that is transferrin, the N-terminal and the C-terminal part of it. So nothing else on that. Now this is studied for the carbon 13 NMR as well as the 27 aluminum NMR of this for a transferrin moiety. Okay, so half molecules reveal high affinity for Fe3+ binding sites in these proteins reside in deep interdomain clefts, and that the metal ion is bound in a ternary complex to carbonate and the side chains, both the carbonate and this. So when it binds to that, you have, so this is basically the OTF, and in the C-terminal region, in the N-terminal region, you can see that. So in the N-terminal region, the chemical shift of the carbon is different from the C-terminal one, and in normal you have both C-terminal and N-terminal kind of thing. Here aluminum also similarly, you can look at this side peak is from the aluminum coming from the C-terminal binding side, and this is coming from the N-terminal binding side. In fact, when the aluminum binds to carbonate, phosphates, other carboxylates, etc., then you can also have the additional peaks, and you can use those where it is binding, just like in the previous example I talked to you about the calcium. And this basically explains a ternary complex to the carbonate, and the side chains are the four highly conserved and widely separated, one aspartic, one histidine, and two tyrosines. They are binding 4 residues but giving all the 6 coordination distorted octahedral. So that means the transferins not only are helping in transport of iron, these proteins may also remove certain metal ions, unwanted metal ions, toxic metal ions, because they have additional binding sites. So this NMR reveals all that. This NMR reveals all that information that you can do that. So that means you can partly use these transference detoxification because of their broad metal ion specificity, the fact that these proteins are not fully saturated with the metal binding. When iron binds, they are coordinatively not completely saturated because different regions of the protein still can bind to that. Not only that, the same transference you can bind to the because scandium is a hard and the oxygens are hard, so hard interactions are good. The carbonate can bind through oxygens, hard oxygens, etc. is a good example. This is done at different the magnetic fields, and you know the magnetic field changing will change the precision frequency change. So therefore, that is what is written here, the 72.9, 97, 121. So the same nucleus, scandium 45, but at different. So how do you get different frequencies? By changing the B value, that is the external magnetic field. You can see just by doing that, changing the external magnetic field, a broad spectra of the scandium bound to this transferrin now start splitting into two, into sharp. You can make all of these. This is what is explained. So additionally, besides the iron binding, you can also have the scandium bound, scandium 3+ bound to the carbonate and to the oxalate adducts. These are all gives a different chemical shifts, and then areas will talk to you about the ratio of these things. So we observed any site specific preference to scandium 3+. I mentioned earlier to site specificity for calcium NMR, whether calcium is bound to 6 or 7 or 3 or 4, whatever is the nearest, and whether they are oxygens, whether some other kind of ligands, all of these will shift. Similarly for scandium also the same kind of thing. That is why the NMR is vital, and in spite that these are solid state kind of an NMR, even in solution, still they are very broad, but unless you use the additional techniques that we already talked to you. So these are the kinds of things that these, obviously the widths are these because of the large the values of these parameters that you have, nuclear resonance frequency, increasing signal, so analogous complexes owing to their large chi value, susceptibility values. So the greater the susceptibility kind of thing, the greater is the influence of this one. So the magnetic properties obviously the influence. Using these techniques which I mentioned in the previous class, all those things you can bring well resolved spectra, reasonably well resolved spectra of that, and then areas can be quantified and then use it. Okay. So and with this we have looked at a large number of examples of solid state and different kind of a nuclei, the silicon, the aluminum, the calcium, the scandium, the carbon, so many different kinds. Many more are possible in these things, and you can study. Now let us transit to another part of the NMR spectroscopy of inorganic, that is the paramagnetic NMR. So I have already explained to you initially the paramagnetic NMR comes because of the transition metal complexes where the transition metal ion having an unpaired electron itself. What will it do? It can broaden the spectrum, it can shift the lines, it can do both of these as well. So that means broaden and shift the lines, otherwise confined to a small range which is called diamagnetic NMR. In fact, when there is a paramagnetic impurities, diamagnetic samples, when people have measured NMR spectrum shows shabby lines. Then they said that something is wrong with the spectra, and therefore they threw the spectra. But it's not true. It's because of the impurity of the paramagnetic species is present, then those shifts and the broadening has taken place. So how will it happen? So the paramagnetic species can interact with the nucleus of spinning nucleus either by scalar or contact through bond, or the dipolar non-contact in the space. So dipolar or pseudo contact, this kind of thing. So dipole interactions or spin interactions. So one spin is coming from your electron, unpaired electron, and that's also in the magnetic field. So huge magnetic paramagnetism, and that magnetic vector or chi can interact with the chi of these nucleus too. Of course, besides the nuclear interaction, they are there. So therefore, this odd electron can transfer its magnetic information either through bond or through space. So that is where, and that can lead to the shifting the signal or broadening the signal, etc. The broadening happens because if the rate of relaxation of this electron, paramagnetic electron, is very fast, that means the rate of the relaxation of that under the magnetic field, if it is very fast, then that will couple with the nuclear spin, which is very slow, and therefore it becomes very broadened line. Okay, and so that is how you get the broadening of that. And through bond or through dipolar, the shift interaction of the magnetic spin at the nuclear spin can give the chemical shift moving. So therefore chemical shift, shifting the chemical shifts to a large and making the lines broaden, that is what the quality of this you can get. So you can see the example here, the phenanthrene. If you just look at the phenanthrene alone in NMR, comes between 0 to 8 or less than 10, and very nice peaks. Now if you take complex of this with the iron, complex of this, and that is the spectrum. So you have peaks coming at 20, 30, 50 and even 100 ppm, and this is again the proton NMR spectrum, not the some other nucleus at all. So you can see that the proton nuclei, nuclei present in these ones when bound to the iron 3 plus, which is paramagnetic, which has got unpaired electron, influences different extents. So that depends upon the distance between the paramagnetic electron to that nuclear which is spinning, not only the distance, orientation of that vector with respect to the external magnetic field, okay, all of these, and through bonds, through space. So all of these will make, so therefore you can have a broad, you can have a shift, a large shift. The shift can be positive, can be negative. Why? Because that electron, the paramagnetic parameter influence at the nucleus can deshield the nucleus or shield the nucleus. So when it shields the nucleus, it will go to the negative side. When it deshields the nucleus, it will go to the positive side. So you can find minus range to plus range, a lot of these things. So you have seen this. Let us look at another example here, the Salon kind of thing. This is a nickel complex. Take just the ligand alone. This is the spectrum. And this nickel complex, 1:2 complex. Then you have your things beyond this. So beyond 75, 80 ppm, 90 ppm and things of this kind. So both broadened and the shifted kind of spectra. Look at very simple case, CH3NH2. So where will it come here? And this is the TMS, this is for the NH2, this is for the CH3, the proton NMR of this. Within 3 ppm you're getting. Now if you put some nickel ions into that, nickel ions, you just dump into that methylamine, just dump a little amount of nickel ions, you will find a peak which is around 80 plus and which is minus 100. So you get both, one positive shift, a sweep towards this, another is, there are only two centers, one is a methyl center proton, other is the amine center proton, and the amine directly binds to the nickel, and the nickel paramagnetic vector will shield the hydrogens of the nickel but deshield the hydrogens of the methyl because of the orientation of the vector with respect to the orientation of the vector present at the nucleus which is spinning, which is under the measurement. So you can get minus or you can get plus. So generally this broad peak come from the relaxation rates. I hope that part is somewhat clear to you in this where the paramagnetic. So we come across a lot in the inorganic chemistry, in the bioinorganic chemistry, a lot of complex, every transition metal complex. So you will have in some stage or the other there will be a paramagnetic. So therefore your spectra will be very different. So one needs to learn how to interpret the paramagnetic NMR coming from the coordination complexes as compared to their ligand spectra. Let us look at probe the causes of this. We already looked at, we said that interaction between them and through bond, through space, dipolar coupling, all of this. And if you try to analyze with respect to the transition metal, you will understand that whenever you have a ground electronic state which has a degeneracy, like for example when you have a T2G1, T2G2 when you have the capital Tg state of the electronic states, then you will find definitely a kind of a shift. Or when you have a high rate of the electron relaxations, also you will find all of these. Or when you have a zero field splitting, the degenerate, the dxy, dyz, dzx, when this splits into the non-degenerate kind of a things, when splitting, then again also you will have when there is no magnetic field, that's called zero magnetic field. Even under that situation also you will find that you will have the shifting for the paramagnetic. That means the D1 can show one electron in the 3, D2 can show that they can fast exchange their orbital, and we have already studied this in the magnetic susceptibility case. We have already studied, and there is the ground state magnetic susceptibility is adding, which is called the orbital contribution of that. So that orbital contributions to the magnetic susceptibility, with respect to the magnetic susceptibility of the nucleus, these will interact, and therefore they can make shielding or de-shielding. And if the rate of the relaxation is fast, then be broadening. So that is where D1, D2, like vanadium 3, tungsten 4, D4 low spin. So D4 low spin also can show, and then low spin chromium 2. So chromium 2 is a D4, and the low spin of that can show. Or low spin, high spin manganese 3 can also show in that, rhenium 3, osmium 4, all of these. D5 systems when low spin. So okay, you can see D4 low spin, D5 low spin, and D6 high spin. So all of these can show because they have the degenerate kind of things. And some of the systems can also show even if there is no degenerate, if there is a zero field splitting like molybdenum 3 and rhenium 4. So you didn't need to remember this? No, because you already know from the coordination chemistry these electronic configurations, and using the electronic configuration you can predict. So in all these kind of situations, your coordination complex is going to bound to show paramagnetic NMR, and at times it may show even a broadened NMR if the relaxation rates are very fast. Okay, so as I already mentioned to you, the local magnetic field due to unpaired electron density would influence the nucleus by showing a large shielding or a de-shielding effects, which results in a large negative or large positive shifts. So these already theoretical calculations are there, etc., which is not a part of this particular course, and then you can guess how they are causing a shielding or they are causing a de-shielding. That means who is causing? It is the electron paramagnetic vector of that, its magnetic moment, its magnetic vector, its chi, influencing the chi of the nucleus like that. So all these arises because the electron magnetic moment interaction with the nuclear magnetic moment through bond, scalar coupling, and spin polarization and spin transfer through bond, either sigma or pi. So you can have a ligand to metal, we have seen that, and that could be from the sigma, but generally much less, but pi a lot. And you can also see the metal to the ligand, we have already studied all that. So ligand to metal, metal to ligand, all these charge transfer will vary your interactions of this, and they can happen through the bond of sigma or pi type, or they can happen through the dipolar coupling or pseudo contact type. So all of these will result in for your molecule as a paramagnetic NMR. So any metal ion with unpaired electron can bring paramagnetic NMR. And if you look at metalloproteins, a huge number of iron based, copper based, nickel based, manganese based, so and all of these, of course, other than zinc, because zinc is diamagnetic, zinc 2 plus. So almost all other will have the cobalt, nickel, iron, copper, and manganese. So all of these will have. So therefore you have a large number of the paramagnetic related species. Now just take one simple example, one very simple, and which is a very common in proteins of iron, heme proteins of iron, and this is one of the, not from an enzyme but from octaethyl porphyrin, the iron 3 octaethyl porphyrin chloride. It's a very standard the compound which is always used as a control in many other things. If you look at these NMR, you would see the peaks change going from this to this, This is put as a reverse field. These are the positive side, this is actually the negative side, using certain kind of criteria. But anyhow, you can see beyond 40, 50, and this side also beyond 50, 60, and very broad. See, this is the actual signal. When you raise the scale, you will see that there is. So this is coming from this CHs kind of thing, and these are coming from the alpha CH2s, you can see. And a lot of asymmetry is come because the ion center is not in the plane of the 4 nitrogens. It's very much away from it, and that brings asymmetry in these things. And of course, the iron is a paramagnetic center. The asymmetry brings the splitting. The paramagnetic center brings the shift. The shift is not because of the asymmetry. The splitting is because of the asymmetry of that. So you can read. So iron atom is above the mean plane. So you can see the 2 phenyl meta and ortho protons magnetically inequivalent. So all of these, and the phenyl ring rotations are slow at the normal temperatures, etc., and a higher temperature you can get the coalescing. I have not shown that here again. So these are the actual values, but here this is shown with respect to a reverse way, but don't worry about it. Methylenes are dash stereotropic, top and bottom of the molecules are not equivalent. That is why you get the 2 levels of the rings. So the B1, which is this is for the CH3, and this is for the CH2s, and these are for this CH, so etc. So some are upfield, some of the downfield. Some general examples for paramagnetic, for example, if you take the cyclopentadienyl sandwiched compounds, which is called the metallocene, with the iron is well known. Then you have a vanadium, the chromium, the cobalt, and the nickel. So you see that they show in the carbon 13 NMR, some of them shows negative, some of them shows positive. This is for the carbon of the cyclopentadienyl. Proton of the cyclopentadienyl again shows positive range, negative range. So these are all because of the paramagnetic, their influence at the CP ring. Okay. Similarly, a set of 4 compounds here. If this is by chlorides, 2 chlorides here, this molecule is common for all of the spectra, and this part is changing. First one is dichloride case. The second one is this one. The third one is this with the binding at methyl groups here on this. And the fourth one is this with the methylamine things. So all of these you can see either to the negative and the positive side. Here is a plus 50 and the minus 40. And here plus 90 to the minus 10 in that range. So plus minus range you can see, and these are coming from the different protons of the ortho, meta, para, and you can see they are basically shown here, and these are shown as alpha, beta, gamma. You can see alpha, the beta, and the gamma. These are coming from these ligands, and the other one, meta, ortho, are coming from this one. You can just sit and see that. So differently influencing. So even if you look at some proteins like lactamase, which is a zinc one, so obviously this is zinc. Now if you replace the zinc by the cobalt center, you would find a spectrum. This is again for the proton NMR spectrum, not cobalt spectrum. The proton NMR spectrum, which is going up to 100 ppm. So mainly you can see in this range. And if you exchange with the water, all these lines will get disappear. So that means the cobalt center is bound to some residues. Upon water addition, the residues are detached. So you can see here histidine, imidazole, 3 histidines are bound. Now if you add water, the proton in a slightly acidic medium, this will get protonated, get detached. Then the proton signal will go away. So that is where different amino acid binding, etc. you can study. From that you can get the structural features and go back and say zinc is bound to the same. So another dimension which is there is called the paramagnetic shift reagent, lanthanide reagents. These are used in a lot of applications, including these medical imaging processes. So in the imaging, why? Because they have they're paramagnetic, their relaxation rates are very high, the coordination numbers can expand because lanthanides can go up to 8, 9, 10, 12 also, and a number of different lanthanide ions, not only europium, examples are known with europium but with others also. So this kind of molecules bound, 3 means it's a 6 coordinated. There is still a lot possibility for the EU DPM can bind to other centers, particularly hard centers, because these are hard centers. They can bind to different hard centers, okay? And it can be with the europium, it can be with the lanthanum, gadolinium, many things are there. So different kinds of these ligands, and so these are paramagnetic. Therefore paramagnetic effect will be on the tissue. You can study proteins, you can study many things, and that's how you use it. How it happens, you can see here one example. This EUF4D, one of these will be this one. 3 of these ligands, 6 coordinated one. This is used, and you take hexanol, CH3, CH2, 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 CH2OH. And if you look at the normal spectrum, it is just comes with this. So with 0 to 3.5, and most of them coming between 0.5 to 1.5. Now if you add a little bit of europium, of course different levels of europium you can add and measure, but only one example I have shown 6.5. And you see this methyl, which is at below 1, it has come above 1. This methylene, which is around 1.2, will come to 1.6, and this one, so everything is shifted. This is what is called paramagnetic shift. So therefore you can spread so these are all overlap and is difficult to identify, but here they are shifted. And using this kind of a methodology, you can use all of them in variety of applications, okay? As usual in every lecture, every topic, at the end I give the practice session. Here also I draw your attention to the knowledge enhancement by extended practice. So I have already shown you the solid state NMR, and try to take NMR literature data and start interpreting for different transition metal complexes, which I have not shown much. So you can take the data is available and try to understand how the interpretations are going. Similarly, you can take some iron enzymes and look at their NMR, how this paramagnetic NMR is influencing, study that. Please do a practice. And also the last topic which I showed you, this shift reagents and paramagnetic reagents shifting, that a lot of data is there in the literature. So please look into that as well. So do your practice for all of these solid state NMR, NMR with the paramagnetic NMR, NMR shift reagents, which are used in a variety of applications of that. So with this lectures, I close the session on the NMR topic for the inorganic chemistry, and we'll start with another topic in the future lectures. Thank you very much.